Yes, sorry. We can see your Zoom, so you can share your presentation.
Just open the
I'm seeing,
PowerPoint.
I'm seeing Dr. Bushra's. Okay, yeah, okay.
Dr. Bushra, did you stop sharing?
Yes, I can.
Yeah.
Yeah.
Dr. Bushra?
Yes.
Did you stop sharing your screen?
I stopped. I don't have anything.
Oh, okay. Thank you.
Yeah.
I think there's some delay.
Yeah.
That's fine.
I'm still not able to share the screen.
You have share button?
Yes, I
You
do.
can, and you click on it?
It says host disabled participant screen sharing.
You are co-host. Do you have any message?
No.
I cannot see why you are not able to share.
Okay, now I can.
Okay.
Just a second.
So go ahead, please. You have 8 minutes.
Yeah.
I made some changes so everyone can share.
Okay. The screen is visible, right?
Yes. Yes, it is.
Okay. Good evening, everybody. I'm
Okay, so you
Pradiksha.
have 8 minutes to present.
Yeah, sure. Okay. Good evening, everybody. I'm Pradiksha, and the title of our paper is Cloud-Based Network Intrusion Detection System Using Deep Learning Algorithms. The teammates are Archana, Chaitra, Khushi, and Pradiksha Nandini. Our guides are Mr. Shivraman and Mr. Prasad Honavalli. This is how the agenda of the presentation looks like. We'll go through introduction, objectives, related work, methodology, results and discussion, conclusions and future work and references. Introduction. With the growing use of computer networks across different fields and applications, network security has become a major concern. Cyber attacks have increased tremendously and are continuously evolving with size and variety, making it difficult to identify them. And hence, intrusion detection system plays a major role in the industry right now. It is a software application or a device that monitors a network or a host for any suspicious activity. There can be two types of intrusion detection system. One is the host-based intrusion detection system, which monitors one particular host or computer system for any kind of malicious or suspicious activity. And the second type is network-based intrusion detection system, which monitors a whole network for any kind of suspicious activity. On the other hand, anomaly-based intrusion detection system uses machine learning or deep learning algorithms to learn the normal behavior of a network traffic and then detect any kind of abnormal behavior that deviates from the normal behavior and hence alert the user or a system about the possibility of a malicious activity. Our main objectives are to improve the accuracy of the model, to reduce false positive rate of the model, increase the availability and scalability of the model, and hence the cloud-based network intrusion detection system. These are the papers that we referred to during our literature study. All these papers have mostly used NSL KDD dataset for training and testing their model, but this dataset is quite old and has redundant columns. In our research, we have used a UNSW NB15 dataset, and it is as new as 2015. This is our proposed model, which is deployed on a cloud. As you can see, the NIDS is deployed on a cloud and consists of 3 microservices: the train microservice, database microservice, and test microservice. All these microservices run as Docker containers and are deployed on EC2 instances. These microservices, starting with train microservice, is the microservice which trains a particular model based on the data that's present in the database microservice. And the database microservice stores the data that comes in or the network packet that comes in. The test microservice tests the incoming network packet based on the model that is already trained and is stored in train microservice. It should be noted that train microservice and database microservice are regularly updated based on the network packet that comes in. So for every network packet that comes in, it goes and stores in the database microservice. And again, based on that, the train microservice is again run to update the model. All these microservices can interact with each other using REST APIs. These REST API requests can be sent through Postman. And there's a load balancer which directs the network traffic to test microservice. So whenever a network packet comes, it is directed to test microservice, where it can be classified as benign or as an attack. And then it is stored in the database microservice, and accordingly the train microservice is again run to update the model. We have used, as I've mentioned previously, we have used UNSW NB15 dataset to test and train the model. The dataset consists of 2.5 million records approximately. The training set consists of 1,75,341 records. Testing set contains 82,232 records from the different types, both attack and normal. The dataset has 49 columns, which were reduced to 47 later. We have removed the ID column and the categorical column, which classifies a particular network packet as benign or attack. The deep learning model is trained in the train microservice triggered by calling the train API. It then stores the weights of the model. Test microservice uses the model weight stored by train to classify the incoming request when test API is triggered. Moving on, just a second. This is the methodology that we have followed. It is a two-stage deep learning model that we have used for this study. The first stage is to extract minimal meaningful features which best represent the data. In this stage, first we convert the categorical data to numerical data. Then we replace the null or empty or invalid fields with the mean of respective columns. Then we define a function to find the correlation between the features. This is done to remove the highly correlated features and hence do not contribute to the classification that is done by the model. In this case, we have used a threshold of 0.8. So any feature that has a threshold of greater than equal to 0.8 is removed and is not considered for the classification of a network packet. And the final step in this stage is to feed the pre-processed data to the model. The second stage is to classify the input data instance as normal or attack based on the features of the initial stage. That is the first stage. In this stage, we have used a sequential model of dense layers, each layer consisting of varying number of nodes. ReLU, that is rectified linear unit, is used as the activation function for each inner layer. The final classifying layer uses sigmoid as an optimizer. We've used this instead of softmax because we are doing a binary classification. And the last step is, and the last point that I would mention in this stage is that we perform batch normalization and dropout technique after each inner layer to avoid overfitting. The deep neural network algorithm that we tried out with 1 to 4 layers is used with appropriate activation functions at each layer. During optimization, hyperparameter tuning like learning rate, number and depth of hidden layers is done, and number of epochs is fixed after trial and experimentation. The results obtained are compared with models implementing LSTM and GRU, along with ML models like random forest, naive Bayes, and KNN. These are the results that we have obtained. For the results, as you can see, for machine learning algorithms, the highest accuracy achieved of 70% is achieved by logistic regression. And in deep learning algorithms, apart from LSTM, GRU, CNN, we have also implemented DNN, and that gives the highest accuracy of 95.02% with 4 hidden layers. Greater than any other machine learning algorithm that we have tested with. In case of DNN, we have used 100 epochs to mention. And these are the charts that compare the DNN models with 1, 2, 3, and 4 hidden layers respectively. We have compared the accuracy, precision, recall, FN score, and false positive rate. This is the confusion matrix for the DNN model and the ROC curve for the same. And conclusion, Instances of an AWS are used to run the model on the cloud and configure the Docker containers accordingly. We have implemented different deep learning models like deep neural networks, long short-term memory, and gated recurrent unit. Using batch normalization has significantly improved the accuracy of the model. Future work, a proactive model capable of detecting possibilities of any kind of attack in the near future can be implemented. These are the references. Thank you.
Thank you very much for your presentation. Any questions, please? Okay, so if you go back, please, to the results slides. Yes, here. So can you please comment about the false positive? I'm sorry, it's not so not the recall, because I'm looking at the paper. I'm sorry for that. So, and which one like give you a better precision and recall for the detection?
Okay, here you can see.
Yes.
Yes, here the better one, precision and recall. So the grays represent the grays for recall. So the better one is the 4 hidden layers. With the 4 hidden layers, DNN, deep neural networks with 4 hidden layers has the better recall. As you can see, 74.45%. I'm sorry. Yeah, this one, the last graph.
And what is your suggestion to improve this percentage? I think you agree with me that
I think
there is this is, by the way, excellent experiments, because I'm sure you were having lower than these percentages when you started your experiments, but how you would think to improve it? You know that 74, 79, still these can be increased and improved. So what do you suggest so that, especially you conducted several layers and you have now different experiments, how you think that these results can be also even more improved?
I think these results can be improved. So we had limited hardware that we had to work with, so we couldn't go beyond a certain computation power. So that could matter, and more than that, we could have a lot more data than that we already used for this. As I mentioned, there are 2.5 million records in this data set, but we could go for a variety of data, a data set which contains a larger variety of the network packets that could help, and more experimentation, because we reached to this after trying with different, trying different numbers of epochs or different number of internal nodes and different number of hidden layers. So I think that would help in further increasing this.
Thank you, Arshana.
Do you Yeah, I have a follow-up question too. So do you think here there is a trend like going deeper in the terms of hidden layers? Do you think that might improve as well?
That could be one of the factor which could improve it, but not the only factor, is what we think.
What are the other factors?
Like I said, the epochs, the number of nodes that we use in the internal nodes, and a data set that's much more, that has a lot more variety than this data set that we have used.
Can you hear?
Hello?
Yes, we heard the answer. This is amazing. Thank you, Arshana. Dr. Rabab, I think we can go to the fourth presentation.
Yes, please. So the fourth presentation, developing an architectural neural network mode choice model for Sharjah University City. So with Fahim Lotfi and Khaled Hamad. Go ahead, please. So can you share?
Hi, everyone. Hello? Can you hear me, please?
Yes, we can hear
Yes,
you.
I can hear you, and
I'm
we can see
facing
your
some problems with the
presentation.
connection.
Okay.
Yeah.
Okay.
Okay.
You can start.
Okay. Hello and welcome. Many thanks to the conference organizers and many thanks to my supervisor, Dr. Khalid Hamad, for his endless support, effort, and guidance. Without further ado, my name is Fahmiya Lutfi, and welcome all professors and colleagues to this presentation about developing an artificial neural network mode choice model for Sharjah University City in the United Arab Emirates. Okay. The presentation is clear, right?
Yes,
Yes,
I can see
it
your
is.
agenda. Go ahead.
Okay, I'll cover this topic through the agenda. First, I will go over the introduction. Second, we will look at the goal and objectives. Then I will summarize some of the previous studies in this field. After that, I will present the adopted methodology. Then I'll talk about the results and discussions. And finally, I will conclude by presenting the conclusions and future work and give some recommendations. So let's start with the introduction. There are multiple options people can choose when making a trip. These are called mode choice of travel. As we can see in the figure, someone can travel from home to a destination using different modes. The person in the upper part of the picture take the bus, while the person in the lower part drives his own car. As we know, driving car is not a sustainable mode of transportation. It is important to use mode choice models to analyze and predict people's choice of their mode of transportation when making a trip. Why? Because modeling mode choice is typically the third step in the classical traditional four-step travel demand forecasting model. This means it is important for the transportation planning process in general, and eventually helps with keeping high level of service and avoid issues like congestions and lack of parking, etc. So what these models deal with, indeed, these models are complex by their nature because they deal with traveler's choice, behavior, and preference of choosing the mode of travel among the available modes to reach a destination. These models also help determining the market share of each mode of transportation in an area, the number of travelers on each mode. So what are the traditionally used mode choice models? These are logit models, and these models are the most popular and have been introduced by the MIT since the 80s, probit models, and discriminant analysis models. After having a brief introduction about the topic, let's have a look to our goal and objectives. The main goal is to develop a mode choice model for Sharjah University City, SUC, using the Artificial Neural Network, ANN. In order to accomplish this goal, several objectives are tackled as displayed here in this flow chart. Number one is to conduct a preliminary statistical analysis. Number two is to develop and validate the model. And three is to validate our results with the previous studies after revealing the literature. When it comes to the related work, this table, in summary, highlights mainly 3 points. The first point is, when we considered utilizing ANN for modeling mode choice at our university campus back in 2018, ANN models have not been previously used for such a task. This is, of course, to the best of our knowledge. This is still largely true, except for a study by Chow and others published in 2020 for the University of Michigan. Well, the second point is there is an increasing interest in developing mode choice models using machine learning in recent years in cities around the globe. And ANN was utilized for other trip purposes, such as schools, cities, shopping, and freight transport. Okay, the third point is, all in all, artificial neural network success in choice modeling is attributed to their ability to handle a massive amount of multi-dimensional and non-linear data, their flexibility, and their good predictive ability. Well, moving to the methodology part, the ANN model was built, trained, tested, and validated. Prior to develop this model, the flowchart summarizes the implemented steps. Number one is data collection, and the whole sample size that was considered in this study is 4,296 records. This is after the data cleansing process. And then conducting a preliminary statistical analysis, and the input variables were 8 factors and covariates, whereas the output is only one, which is the chosen mode. And this output variable includes 5 different types of transportation, which are car, taxi, shuttle, Sharjah University city bus, and walking. At the end, the model is developed, and the best architecture and the best ANN architecture is the model that consists of 1 hidden layer and 5 neurons, with 5 neurons. Okay, in the results and discussion part, the best multi-layer perceptron neural network was plotted as illustrated in the first figure on the left. The second figure shows a focus on the classification table of the best neural network architecture, with 89.3% for the overall cases that are correctly classified, I mean sensitivity. The third figure displayed a focus on the measure of performance table with 95% model classification accuracy. And the last figure gives an indication and proof that the model does an excellent job in predicting the output classes for each chosen mode for this study based on their 8 input variables. Last but not the least, the variable importance analysis showed that trip duration, car sharing, and trip distance are the most important determinants affecting our mode choice. Finally, several recommendations were drawn. First, for the future work continuation, we recommend developing additional mode choice models using other types of machine learning techniques, and collect a new travel survey data after the COVID-19 pandemic to capture the new travel patterns. For city and Sharjah University officials should take initiatives to promote public transport and car sharing. For the local transportation officials and planners should consider utilizing artificial neural networks models. Here are the list of the references, and thank you.
Thank you very much.
Welcome.
Just a clarification. So how did you collect the data, please?
Okay, actually, data collection process, it was in the academic year 2018-19, the both in person and designing a web-based travel survey. Yeah, so this is how it comes. Designing a web-based travel survey consists of 2 parts: collecting a socioeconomic information about the participants, and also diary or a log to collect the travel information.
Okay, so and then you try to do the analysis of your database on, for example, the gender, is he an owner of a car or not, and so on?
Yes, yes.
Okay, okay, thank you very much. So any questions from the audience?
Can you hear me?
Yeah.
Great. Thank you for the nice presentation. May I wonder, did you use any validation techniques to generalize your designed model for the true error rate?
Okay. We did at least two types of validation. Actually, when we are building the model, I use the SPSS software as a part of the process in order to build and train and test the this data set or this model. SPSS divided the whole data into three subsets: testing, then training, then testing, then validation. So this is the number one, the validation process. Also about after revealing the literature, we compared our results with the previous related works. It's not for the university, but for ANN, utilizing artificial neural networks for different purposes of mode choice modeling.
Thank you.
Welcome.
Thank you very much. So let us move to the fifth paper. Deep learning techniques to detect DOS attacks on industrial control systems, a systematic literature review. The authors are Abdel Karim, Ali Abu Nasif, Qasim Nasser, Bushra Al-Balushi, and Manar Abu Talib. So please go ahead.
Thank you.
You're
You
welcome.
can hear me?
Yes, we can.
Okay. I'm just trying here to share the screen.
Yes, please. Yes, so we can see your presentation. Thank you. Go ahead, please.
Excellent. Thank you very much. My name is Abdel Karim from Sharjah University. Here I'm going to speak about the deep learning technique to detect DOS attacks, mainly on the industrial control system. And this is about a systematic literature review. Okay. First here, we'll start about the introduction and the objectives. Then we speak about some of the related work and the methodology that we have proceeded forward and the result discussion for this systematic literature review. And then we'll speak about the conclusion and future work. Then we'll demonstrate the references. So first, we need to speak about why OT, or the operation technology, or the industrial control system is important here, why we think about cybersecurity. Actually, these critical infrastructure devices or components, before they was not exposed to the internet, and mainly there was closed system. Then once we start exposing them to the internet, we start getting a huge amount of attacks. Mainly these systems considered very critical when we speak about the power system or power grid system, the water distribution system, metro, or different critical systems that are playing vital roles in our life. So here we have actually a lot of papers or researches that discussed the network intrusion detection, but mainly it covers it about the within the field of the information technology or the traditional network. So here are a few papers are looking on the DOS attack on the critical system or the ICS. So within the ICS environment, we have different complexity, heterogeneity, different vendors, and diversity. So we are more thinking about the attack surface that got exposed to the internet due to the interconnectivity of these systems over the cyberspace. So here we need to address following objectives. First, we need to have a reliable and accurate approach to detect those attacks before they occur. So we need to have some kind of pattern. We need to be identified or to be aware or to identify the system that's under attack, or possibly, potentially, that they can be attacked by some specific behavior analysis. Then definitely we need to consider the DOS attack, because within the NIST, or the Institute of Standard Technology, National Institute of Standard Technology, it considered that it has around 45% of the general attacks on the industrial control system. So within this systematic literature review, on deep learning detection, we are looking on a comprehensive view over both type of networks, the traditional information technology networks and the operational technology related to the critical infrastructure field. So here we need, after all, to enhance the classifier efficiency to utilize different source of inputs, not necessarily the available data set. And we need to have more efficient way to detect behavior of those attacks within different approaches that been used on other research paper, and how we can have the best accuracy or best precision on our result. And after all, we need to depend on, there is a question here, can we depend on existing network intrusion detection system? Definitely, it is not similar to the OT network or the critical infrastructure, because within the OT network, we are looking at different protocol, different size of packets, different pattern of attacks. So it is a different way of learning or training our data. And we are looking at using passive monitoring or darknet data set in order to enhance our classifier efficiency, or to train our classifier to enhance the efficiency. So related work, we have different papers discussing the convolutional neural network, and they gave the comments that it takes more computational time, while we know that to detect the DOS attack, we need to have a good timing for testing and to identify training and testing for the system or the algorithm. So there are other papers also looking after the deep neural network, where they conclude that it's less capable in learning time series dependencies, which is very important in identifying the DOS pattern or DOS attacks. And also RNN, or recurrent neural network, which is suitable for temporal data learning and sequential data, but definitely it has the vanishing gradient or low memory. So within this systematic research review on following the Kitchenham methodology, we put 4 questions, and here we need to look at a small comparison about each of the questions. So the first question is about what are the used deep learning techniques for attack identification on the ICT environment. Here I'm putting in the table a small comparison between the papers that has been looked after within the IT field and the OT or the ICS field. And we can see here the most common one within IT or the NIDS, network intrusion detection. It's leading with the approach of DNN. And for the OT environment, the LSTM or the long short-term memory is leading for these deep learning methodologies. The other question here, which data set used for DOS detection in the research article? So different researchers are using different data sets, but we can see most of them has depend on the NSL KDD for number of attributes and capability to train the data for the DOS behavior. And here we can see the data set that has been used, most of it, or around 45%, is looking after DOS attack pattern within these, or attribute within these data set. And the third question is about the common evaluation metrics used in this research paper. We can see the accuracy and the precision is leading here, and also the recall value and the phone score. So these are common evaluation matrices that can be used to benchmark our approach or our algorithm for the deep learning of those patterns. Now, the last question here is about the strengths and weakness of the deep learning techniques, cover deep learning techniques. So the DNN here, it's more scalable, but it has it's weak to learn the time series dependencies. compared with the other techniques. Let's say the LSTM here is the most suitable one because it can predict the time series, and it needs a lot of data. Actually, it has a side work where it needs to have a lot of data and time for training compared with other techniques. So, okay, here for the conclusion here, I just want to discuss about few points that related to this paper and covered in this systematic literature review. It's about insufficient input for malicious training data is a major shortcoming for development and training, and mainly actually for privacy. When you speak about the data set related to the ICS or the critical infrastructure, there are too many big organizations are keeping these data for themselves because it's kind of privacy to expose these data or these data set on the public or on the internet. And they are more related to the manufacturing or factory where they think that this data cannot be exposed, and we have a limited number of public data set to be used for training. And hence they are using another traditional data set that is not actually useful, like the NSL KDD and the DOS dataset. This is a potential cause for overfitting, which is negatively impacting the performance for the model to learn new data. And definitely the DOS attack detection is kind of like, it can have different pattern, and it doesn't have a specific behavior that can be detected. Hence, a zero-day attack for some techniques cannot be possible to be detected, as we need to look after the time series dependencies of these patterns. Okay, another point here, considering the modern data set related to the critical infrastructure protocols to enhance the classifier training and efficiency. So we need to look more into the behavior of the protocols that used on the industrial control system, and definitely the packet size. And the last point here is about considering the cyberspace attack traffic collected from the passive monitoring or the darknet dataset to be used to train our model. That this dataset is very useful because it doesn't have a specific pattern, it keeps changing, and can give overall a good way to or let's say a big amount of data that can be useful to have some kind of zero-day detection for our model. Here we conclude our presentation, and thank you very much.
Thank you very much, Abdelkarim. It's a very, very good work and excellent presentation. I have a question concerning one of your slides. You mentioned that one of the problems was overfitting.
Yes.
For the data, right? And of course, you don't have enough examples of intrusions, basically, like the malicious attacks. You don't have examples of those, and usually they could be one of, like they don't repeat the same. So how about, have you thought about looking at the problem from an anomaly detection problem? And look at what is a normal behavior, model the normal behavior, and then flag anything that is not following a normal behavior. Because a normal behavior, you can model that more precisely.
Yeah, correct. Actually, for the anomaly detection, as you mentioned, that it's abnormal behavior. Here, we cannot really confirm it is related to a DOS attack for a specific type of traffic or let's say a DOS attack in general, because the anomaly detection can be also any false data injection, or it can have possibly different type of attacks, which is, as let's say, if we look at it in a border, in a wide view, yes, it is a good way to identify if there is abnormal behavior or not. Correct.
Maybe a recommendation is to look at some techniques used for detecting damages, actually. This is a very well-studied topic as well in identifying, like, for example, for inspections, to identify damages in machines, for example, or in goods. And there are a lot of really nice, interesting techniques that people are layering multiple algorithms and techniques together, because especially with these malicious attacks, they become very they become very ingenious, and they become very unique at every time, and they try always to outperform. So it's really no attack is equal to the other attack. They're almost unique.
Correct. Yeah, this is very important in this big amount of data. In order to have a good training, we need to have a unique patterns of data to train our model, and a huge amount of data. Yeah. We'll look into that.
Thank you.
Thank you.
Do we have any other questions?
I think, Bushra, just to keep up with the time, we should move on.
Yeah. Yes. Okay. So are we done now? We should be moving to the next, because we did not take a break. I believe.
Yeah, we'll skip this break.
Yes.
And, hopefully.
And then, okay, so we will start with the next section now. So the next talk is accelerating neural architecture search with rank preserving surrogate models by Hajar bin Mizyan, Hamza, and Kautar Maghrawi, and Ismail Niyar. So who do we have who's going to be presenting?
I'm here. I'm Hajar bin Mizyan.
Hajar.
Yes.
Okay, Hajar. Thank you. Okay, we can see you and we can see your presentation. Please go ahead.
Okay. So, okay. Hello, everyone. I'm Hajar bin Mizyan, PhD student at l'AMI, Université Polytechnique des Hauts-de-France, and I'm glad to present our first work in the path to accelerate neural architecture search with rank-preserving surrogate models. And this work is done with IBM research.
Sorry, Hajar, to interrupt. We don't see your slides. I don't see your slides.
Abdelkarim,
I think that we are still seeing the, yes,
No,
the slides of
previous one.
Abdelkarim.
Abdelkarim, can you stop sharing?
No, I do see his, I do see Hajar's slides, actually.
I don't.
Okay.
I still see, yes, now I'm seeing the slides of Hajar. Thank you.
Okay, I see Hajar's slides. Okay. Please go ahead, Hajar. Please go ahead.
Okay. So I'm glad to present our first work in the path to accelerate neural architecture search with rank-preserving surrogate models. And this work is done with IBM research. So in this presentation, I'll first start by motivating the use of surrogate models in neural architecture search. Then I'll present our new training methodology using ranking loss. And finally, I'll discuss some of the results we have, and I'll conclude with some future work. So as we all know, with the rise of edge computing and the Internet of Edge, there's a lot of applications out there that we can use at the edge by running AI or deep learning models in the user's own devices. But the problem, despite their increasing accuracies, current machine learning architectures are too large and too complex to be deployed in such devices. So we need new ways and new search algorithms to create and design architectures that are small and fast. And hardware-aware neural architecture search is one solution to that. Now, the general structure of hardware-aware NAS is composed of three main components. The architecture search space that defines the set of architectures we're looking at with the different operations, the convolution, the pooling, the activation, etc. The search algorithm that looks into the search space and tries to find the best architecture, and the evaluation methods that provide the accuracy and the hardware measurements needed to compute the objective function and thus orient the search algorithm to the best model. Now, although this kind of methods and this kind of process helps us find state-of-the-art models like ArabWIC. It is really extremely time-consuming. So to find ArabWIC, for example, it took 75,600 GPU hours. And the components that takes a lot of time is the evaluation. So in our paper, we try to accelerate this evaluation. As we all know, training a ConvNet architecture, a CNN architecture, takes 2 to 3 hours minimum on ImageNet. So training 1,000 of architectures sampled from the search space will take extremely longer time. So fully training the architecture is not an option. Now we have other options to remedy this issue, like partial training, where we train our architecture for a few epochs only. Proxy dataset, where we train our models for a smaller dataset, and then once we find our best model, we just transfer it to the larger one. Or maybe learning curve extrapolation, where we train our model for a few epochs and then try to extrapolate the accuracy after more epochs. And finally, we find surrogate models. And surrogate models leverage machine learning algorithms to predict the accuracy directly from the architecture characteristics. So we have the architecture characteristics, we feed them into a model or a machine learning algorithm, and we get the predicted accuracy of the architecture. While other evaluation methods use some training in them, surrogate models don't. So we have a speed up of the NAS process from days to only a few hours, and this is really exciting. Now, we noticed this error when using surrogate models. So let's suppose we have this surrogate model that is trained with the MSE loss to predict the accuracy, and we have this gray and blue architectures. And we know from fully training the two architectures that the gray one is better than the blue one. So we have 95% and 92%. When using our surrogate model, we get accuracies that are close enough to the real accuracies, but we have this rank error where the blue one is now better than the gray one. And this prevents the NAS process from getting to the optimal architecture, because it will, during the search, it will search for architectures that look like the blue one rather than looking for architectures that look like the gray one. And in the literature, we find several surrogate models like XGBoost and JGraph isomorphism network that are trained on NAS Bench 301, where this error occurs an average of 5,000 times per sampled architecture. Now, to avoid this problem, we leverage the learning to rank theory to train our surrogate model. We call a discordant pair a pair of architecture where the rank error occurs. So like the gray and blue architectures here. And then we compute the distance between a discordant pair as the distance between the two predicted accuracies if the pair is discordant, if the pair of architecture is discordant. And we compute this new loss that we propose, which we call the RMSE discordant, which is the sum over all the distances between the discordant pair in the batch. And here we have like some correlation results that help us to decide which loss function we're going to focus on and which machine learning algorithm we're going to use. So to evaluate our models or our results, we use ranking correlations that are the Spearman correlation and the Kendall-Tau correlation. So these correlations evaluate if our model, if our results respect the ranking of the variable we're trying to learn. Now, to find our best loss, we tried to compare our RMSE discordant with the standard RMSE used to predict the accuracies, and with a linear combination between the RMSE and the RMSE discordant. And we find, of course, that with our loss, we get a Kendall-Tau correlation that is really close to 1, which is really good. Now, an interesting result is when fine-tuning. So we took a model that is trained with the RMSE to predict the accuracies, and we trained it a little more with our RMSE discordant. And we find that the model preserved the accuracy prediction while having a better ranking correlation. Now, to find our best algorithm or best model, we compared 5 different machine learning algorithms: MLP, XGBoost, LGBoost, graph convolutional network, and graph isomorphism network. So overall, we can see that all of them, when trained with our ranking loss, perform better than when trained with the standard RMSE. And we can also see that XGBoost or boosting trees in general perform better than graph neural networks or standard MLP. So we used our final XGBoost models that is trained with our ranking loss, and we use it to speed up the search algorithms in different NAS benchmarks. So, and we can see that here, for example, our results are in blue, and compared with a standard surrogate model that is trained with the RMSE in red. So we can see that overall, in all the experiments with all the search algorithms and different benchmarks, we can see that we find a better model, a final better model with better accuracy. Now in NAS Bench 101, we used our surrogate model in an evolutionary algorithm to compute its fitness function. And in NAS Bench 301, we use it with reinforcement learning. And we can see here a really interesting result where a local search on darts, we can find an architecture that is 4% better in accuracy. Now, to conclude the presentation, I would say that we believe that NAS is an important tool to find efficient deep learning models. We believe that surrogate models will help accelerate NAS process and allow us to explore bigger search spaces and find better models. And to our main future work is to develop a multi-objective surrogate model to enhance hardware-aware NAS in general with the hardware measurements and the accuracy measurements. Thank you. And here are the references.
Thank you, Hajar. Very, very good and excellent work and nice presentation. Are there any questions? I actually have a question for you, Hajar. So this is very, very interesting in trying to reduce kind of like the size and the training of these very large algorithms, especially the deep learning algorithms, and fit them into hardware and edge devices. What is, in your opinion, what is the trade-off? There is always a trade-off, performance and accuracy, but accuracy and precision and recall. What is the trade-off that you're willing to give away for some specific applications? Because again, you cannot get higher precision and high recall at the same time.
Yeah, so
because that's looking at it from that rather than just the accuracy, because the accuracy could be misleading sometimes.
Yes, exactly. So in this first work, we try to we try to validate our theoretical informations, and we just do the evaluation with the image classification, where we can use the accuracy to evaluate our models as a task. It's not like a real practical task where we do image classification in autonomous driving or in other situations. And we on our future works, we want to include some more tasks and go to object detection and image segmentation.
Okay, thank you. Any other questions?
Excellent job, Hajar. I'm very impressed, and I saw that you have a GitHub link. Did you get any feedback from the community, and what was the role of IBM in your research paper?
So for now, I didn't get any contribution in the GitHub link yet. What I did in the GitHub link is that I shared all the code, and I shared the models to use the surrogate model in any NAS work or any NAS work the community is willing to contribute on. For IBM, Dr. Kautar Marawi is my supervisor. So she's helping me with guidance and advice all along the creation of this project.
Thank you, Hajar. Bravo.
Very, very nice. If there are no other questions, we can move to the next talk. So the next talk is predicting the diagnosis of dementia from MRI data, added value to cognitive tests. And that's from Tatiana Habuza, Nazar Zeki, Yawen Statsenko, Fadi Al-Hajjar, and Sana El-Yasami.
Hi, can you hear me?
Yes, we can. Can you share your screen?
Yes, I've already done it. Can you see my screen now?
Yes, I can see it. Others can see it as well? I can see it.
Yes, we can. Yes.
Yes,
we
loud
can.
and proud.
Okay.
Very good.
Yeah. Okay. So thank you for your for the opportunity to present our work here. My name is Tanya. I'm a PhD student at the United Arab Emirates University, and we're also working at the Big Data Analytics Center here at the UAU. And one of our research interests is related to the brain aging, specifically to the patterns of normal brain aging and accelerated aging. So this talk is going to be devoted to the predicting of the diagnosis of dementia from MRI data, added value to cognitive tests. Our agenda for today's talk is as follows. We'll start from the motivation, then introduction, related work, in objectives. Then we'll move to the methodology. Specifically, we'll stop at the data set we use, and then the pre-processing techniques. And finally, we'll go through the pipeline of our proposed method. Then we'll move to the experimental work and result, shortly discuss them, and finally conclude and show the future directions. So let's get started. The problem of aging and age-related diseases is very common, and worldwide population faces this problem nowadays. For example, here in the UAE, the life expectancy increased by 4 years in the last 20 years. It means that the importance of studies covering the neurodegenerative disorders is high, and many researchers are attracted by this problem. Neurodegenerative disorders are the conditions which result in neuronal loss, brain atrophy, and progressive deterioration, which is dementia. And dementia is characterized by the devolution in memory, thinking, behavior, orientation in space, justification, and some ability to perform everyday tasks. So it's one of the major causes of disability among older people. Alzheimer's disease is the most common form of dementia. Interesting that by the time that the person begins to experience the symptoms of the disease, its condition is already well established in brain. It means that brain imaging actually could serve as a subtle marker of a disease. However, now the diagnostics of dementia are mostly done with the help of cognitive tests. This task is challenging, and because there is no standardized test, as well as it's very time consuming. We think that it could be good if we use both function of a brain and its structure. So our hypothesis is that the diagnostics of dementia can be improved by studying the association between the structure of a brain and its function. And definitely machine learning and deep learning techniques may help in this task. So what is happening in the literature so far? Many of the researchers trying to predict the dementia or the final diagnosis, as it's written in the table number 1, from the images of, or MRI images of demented and cognitively preserved population jointly. But again, as dementia is associated with structural and functional changes, we think that modeling it should be based on both neurophysiology and neuroimaging. And some of the papers here use this structural functional association to predict the diagnosis. However, our approach is different because we think that the clinical value of such models is limited. We propose to build the model based on only normal people or cognitively preserved population, and then later on look at the gap between the predicted and actual value in terms of cognitive tests, this gap may be a marker of a neurodegenerative disorder. So our main objective here is to find the possible relationship between structure and function, or between cognitive performance and predicted cognitive gap. We denote here a predicted cognitive gap as a difference between the predicted and actual value of cognitive tests, or cognitive test results. Looking at or addressing our main objective, we can have few subtasks, specifically to conduct the exploratory analysis of the data, then move to the calculating the cognitive gap from the designed convolutional neural network based regression model, then and finally to justify the proposed predicted cognitive gap as a screening tool for dementia, and provide some comparative analysis of different cognitive tests, as far as there are many tests used in detecting or diagnostics of dementia. So let's move to the methodology part. As far as we're working with the images as a structural part of our association, that structure is represented with the help of T1 weighted MRI images. We acquired that images from the Alzheimer's Disease Neuroimaging Initiative dataset, which is publicly available by request. And we acquired from there almost 800 cases with the distribution shown here. That dataset also includes some clinical information on final diagnosis, some demographic data, morphometric data, and some cognitive assessments data, which are specified here. The next step, what we did from the with the acquired MRI T1 weighted images, we pre-processed them more. So we registered all the images to the MNI152 space. Then we conducted some N4 bias correction. Then we moved to the normalization to normalize the intensities of the voxels, extracted the brain tissues, and finally performed the background removal. So what is left is only the brain tissues. Then, to move forward, we decided to reduce the dimensionality of the data in this specific work from the 3D to 2D. So how did we do this? If we define the MRI image I as is specified in Formula 1 as a 3D image of voxels, then each and every space or plane, sagittal, corneal, and axial can be specified with a specific voxel. And then each and every slice on that specific plane can be specified with the formula number 3. So in our study, this one, we used only axial slices. And what did we do with them? We composed two data sets. The first data set was composed by averaging all the slices as axial or biaxial plane.